A cart carrying a rider is traveling at half the speed of light, 0.5 c, in a vacuum. This means the cart is traveling at 150 million meters per second, whereas the speed of light would have been 300 million meters per second. Assume the situation takes place in a medium that is essentially a vacuum. What's happening here is a person riding on a moving cart is going to throw a ball toward a catcher. The catcher is stationary on Earth. So this is the thrower A, and this is the observer B. The rider of the cart is going to pitch a ball toward the stationary observer. When the ball is in motion, which choice below is most accurate? Would it be true that since the ball is moving very fast, then the light waves and light particles leaving the ball have to be traveling faster than light speed? Would they be traveling faster than 3 times 10 to the 8th meters per second? Or is it true that light always travels at 3 times 10 to the 8th meters per second no matter what in a vacuum? Well, the answer, according to Maxwell's findings and also according to Einstein's postulates for relativity, the case must be B. Light always travels at 3 times 10 to the 8th meters per second no matter what the speed of the emitting body is, and even no matter what the speed of the observer is too. Light always has to travel at 3 times 10 to the 8th meters per second no matter what the velocity of the light emitting body is. Not only that, but the person receiving the light has to see it coming toward their eye at 3 times 10 to the 8th meters per second. And even the person at A, who's traveling at half the speed of light, they still have to see light coming at them at 3 times 10 to the 8th meters per second. This is what Maxwell's findings imply, is that there's no other speed other than 3 times 10 to the 8th meters per second that light can travel. And the reference frame that you're in doesn't matter. So whereas observer B is in a stationary frame, let's say call it S, A, who's moving, could be in a frame S prime, and the speed of the frame is 0.5 c. And regardless of the different frames that these observers are in, they will still both have to see light coming at them at speed c. Now, Einstein thought about this idea, and he came up with this thought experiment. He tried to imagine what it would be like to travel at the speed of light. So imagine Ted, who's riding on a beam of light. Say that Ted is riding on a light beam, and he also holds a flashlight which shines a light beam of its own. Ted is traveling at light speed, speed c. And the light beam emitted from his flashlight is also traveling at speed c. How does Alice see this situation? She believes that Ted is traveling at speed c. But what is the speed of the light beam that Ted is shining? Well, according to Galilean relativity, you would think it would be 2c. If the flashlight's moving at speed c, and then a beam of speed c is being emitted from that flashlight, then you would think, according to classical physics, according to Newton, and according to Galilean relativity, it should be 2c. But what Einstein says is that nothing can travel faster than the speed of light. Therefore, she will actually measure the beam from Ted's flashlight to be traveling at speed c. So bring that back to the situation above for a moment. If the thrower is traveling at 50% of the speed of light, and let's say the thrower throws this ball at 0.7 c relative to himself. How fast does the observer B believe that that ball is coming at them? So, according to classical physics, the answer would be 1.2 c. But Einstein said that this can't happen. We would actually have to do relativistic transformations to find the speed that B will measure the ball with, and it won't be as big as c. No object of mass can actually travel at speed c. Einstein showed it would require an infinite amount of energy to accelerate any object of mass to light speed. So instead, what will happen is, even though A sees it as traveling at 0.7 c, B will actually observe the ball traveling at a different speed, which is less than the speed of light.